Good evening. This will be the last of the thermochemistry lecture videos covering Gibbs free energy. In this video, we will talk about how to calculate Gibbs free energy using a few different methods, showing the relationship between work and Gibbs free energy and equilibrium. After talking with a few people in class the other day, I wanted to clear up one little thing that was confusing a little bit of people, which was dealing with the sign that we would have for the delta H in the equation. So when we're talking about delta S of the surroundings, we can relate that to the negative amount of Q from the system. So remember, we talked about the fact that the heat content, because it's flowing from one object to another, hotter to colder, whatever the Q for the surroundings is, it would have to be the negative Q for the system, or the opposite. So we can term the delta S for the surroundings as the negative Q divided by T for the system. And we know that if we have a constant pressure situation, that the amount of heat energy Q would be equal to the enthalpy delta H. So we can say that the Q for the system is equal to the delta H for the system. And then that becomes delta S of the universe equals delta S of the system plus a negative delta H for the system over T. So again, using the relationship that the delta S for the surroundings would then be equal to the negative delta H for the system divided by the temperature. So now I have everything, both the delta S and the delta H, in terms of the system. So if I multiply both sides by the negative delta T, that gives me the negative T delta S for the universe equals negative the delta H of the system minus T delta S for the system. This part here is what we can then term as our delta G. So again, if I have in this case a negative delta G for the value, then that means that I have a spontaneous reaction. So when the negative T delta S of the universe is a negative value, then that means that the process is thermodynamically favorable. So again, when negative T delta S is less than 0, we are thermodynamically favorable. To use the correct College Board terminology, I have that thermodynamically favorable reaction or spontaneous reaction. So I hope that clears up any of the confusion that was coming from that last video. So we have three possibilities for the values for Gibbs free energy. If we look at the delta G being a negative value, then that means that the forward reaction would be spontaneous or thermodynamically favorable. If delta G is equal to 0, then the system will be at equilibrium. And if I have a delta G that is positive, then that means that the forward reaction would be thermodynamically unfavorable or non-spontaneous in the forward direction, but that would mean that it would be favorable in the reverse direction. The free energy for a system is defined as the maximum possible useful work that can be obtained from a process at constant temperature and pressure that is equal to the change in free energy. So when we look at this, the delta G for a process, remember that if work is done by the system, then you have a negative work. So if I have a spontaneous process where I have a negative delta G, then that would provide a negative W for the value. The thing that you can think about is that when we talk about this component of useful work, that's essentially telling us how much real work we can get done by a system on the surroundings. So the easiest example I can give you for something like this would be your cars. If you think about having a 20-gallon tank in your car, typically only about 30 to 40% of the gasoline in the more modern engines, and it's sadly even less than that, roughly around 20-25% in some of the older cars, actually is used to make the car move forward. the majority of the energy is lost as heat. So you can think about the delta G as being, or that free energy being, the amount of work that actually does something for us that's not lost as heat. So just like delta H, we have a number of different possibilities for calculating the amount of free energy within a system. The first of which is just the standard free energy of formation. So just like the delta G, just like the delta S, we can solve for the standard energy of formation for the products and multiply them by their coefficients, and subtract the sum of the delta G for the reactants multiplied by their coefficients. So you have that standard products minus reactants for the standard free energy of formation. So just to reiterate one more time, when I had that little degree symbol, that stands for 1 atmosphere of pressure, 25 degrees Celsius, your standard state conditions that we would see. You have Hess's law of summation that can apply to delta G reactions as well. So just like we had the delta H reactions where we had those multi-step reactions where you could take all the reactions individual energies and multiply or add them together, we can do the same thing with delta G. And so it works the exact same way. You can multiply a reaction to get the right coefficient. You would then multiply the delta G value. If you flip the direction of the reaction, multiply it by -1. So you can use the Hess's law of summation. We also have the standard most common form, which is to relate the amount of entropy and the amount of enthalpy within a system, and that is your Gibbs free energy equation, delta H minus the T delta S. This one here, again, is occurring at a constant temperature. So just remember that that temperature must be in Kelvin. So this is all the stuff that you should have learned last year at a minimum. And the fourth and the fifth are the new ones that really kind of define the difference between the honors chemistry class and the AP class. So we can relate the standard free energy change for a reaction to the equilibrium constant, and we can do that with a negative RT ln K. You can just kind of think about that as a negative rat link as a easy way to remember it. But we can take the R value, always the energy unit, so that's the 8.314 joules per mole Kelvin, and then whatever your temperature is, you can multiply that times the ln of K, and again take the negative of that, and it will tell you the delta G value. And then finally, we have a fifth method that we can use, which we will look at in depth next unit, which is the delta G equals a negative NFE. So in that type of situation, what we're trying to do is calculate the free energy that would occur within some type of battery. So that's the cell potential, looking at voltages. And so we can multiply the number of moles, which would be your N. The F is the Faraday's constant, and then the E is the electrical cell potential, which we would look at from a standard list of values. So that is the fifth method. We will cover that next unit and wrap up the equilibrium concept and the thermodynamically favorable concept to these creation of the batteries. So we're now going to look at a couple of example problems for each of the different types of scenarios that can take place here, and we'll wrap up this unit. So for our first problem, we're going to calculate the standard free energy change from the free energies of formation. So you would be having this data appear either in a table, or you could look it up in the back of the book in one of the appendices, and you could get all these different values. So I just went ahead and listed out what the values are approximately for these different substances. Please remember, just like delta H, unlike delta S, you have the delta H of formation for your elements being a 0. So again, I'm just going to use my basic equation here for this reaction, delta G for the reaction is equal to the delta G for the products, again multiplied by their coefficient and taking the sum, minus the delta G for the reactants. So in this particular instance, I have a delta G, and I just like to make it a nice little tabular form, delta G for products and for reactants. For my products, I have negative 394, and I have 2 times negative 229. So my total here for these, 2 times negative 229, that's negative 458, and 394, so I believe that should be negative 852. And then for my reactants, I would have negative 51 and 0 times 2. So I'd have a negative 51. So I could take negative 852 minus a negative 51, so that's plus 51. So that would leave me with a delta G value of negative 801 kilojoules per mole reaction. So we want to determine the spontaneity of the reaction, or the thermodynamic favorability of a reaction. We can base it off of the values for delta H and delta S. So we want to be using the equation delta G equals delta H minus T delta S. Whether or not a reaction is favorable or not oftentimes depends on the temperature. So again, as we've said before, the temperature can affect that spontaneity. You think about some easy processes, something like melting ice. If the temperature outside where the ice is 25 degrees Celsius, then it will happen without us having to do anything, and the ice will melt to form water. It has enough energy in the atmosphere to make that happen. If, however, the temperature's, say, minus 10 degrees Celsius, then I could take that piece of ice out of the freezer and it would stay just as that nice little piece of ice on the table or street, whatever it happens to be, and it won't melt. So when we talk about that temperature dependence, it can be spontaneous in one direction at a certain temperature, but if we change the temperature, it no longer is spontaneous. And so that's one of the hard things about this type of situation, but also one of the nice things is we can determine what that temperature is when the reaction changes from being thermodynamically favorable to thermodynamically unfavorable in that process. So when we look at the different combinations, we want to compare the delta H versus the product of the negative T delta S. And so as we're making these comparisons, think about how this value would affect the reaction. So in the first case, where I have a positive delta S and I have a positive delta H, remembering that the delta S is in joules per mole Kelvin for the reaction, and delta H is in kilojoules per mole of the reaction. So we have to make our conversions because delta G is also in kilojoules per mole of reaction. We need to convert the delta S from joules into kilojoules to make our appropriate relationships. So when I look at delta S being positive and delta H being negative, again, just want to have you think about that scenario. The thermodynamically favorable process is when delta G is a negative value. So in this case, if I had a negative for the delta H and then I subtract a product of the T delta S, with that being a positive, remember temperature in Kelvin, always a positive value. So if I had a negative subtracting a positive, the only option that I have is for the delta G to be a negative value. And so it will be spontaneous at any temperature. I could have a second scenario where I still have delta S being positive, but now I have the delta H as a positive as well. So when we talk about that spontaneity, from an enthalpy standpoint, the more favorable process is the exothermic process, but from an entropy standpoint, the more favorable process is a positive process. So I want to have, in this case, because I have two positives, and I have a positive subtracting a positive, I now want my T delta S product to be greater than delta H. And so we talk about that happening spontaneously at high temperatures. Well, if it's not a high enough temperature, then delta H would be greater than the T delta S, and delta G would be positive. So at low temperatures, under those conditions, delta G would be a non-spontaneous process. I can have a third situation where the delta S is negative and the delta H is negative. So I now have a favorable exothermic reaction, but I have a unfavorable disorder component to it. So in this situation, now because my delta H is a negative and I'm subtracting a negative, so that would be adding, I want to have my temperature being low. So this reaction would be spontaneous at low temperatures because now the delta H is the dominant feature for that reaction, and it would be non-spontaneous at higher temperatures. And then finally, we have one last case scenario where I would have, in this situation, the delta S being negative and the delta H being positive. That again, I'd have a positive subtracting a negative, so I could never have anything but a negative value for delta G. So this process, no matter what, would be non-spontaneous at any temperature. Now, I hope there's one question that's coming to your mind at this point. And that's simply, what's defining something as a high temperature? What's defining it as a low temperature? Well, that is going to depend on the particular process that we're studying. And so there's a really easy way that we can figure this out. If you think about the condition when delta G is equal to 0, that's at equilibrium. As soon as it goes slightly below 0, it's now spontaneous. Anytime it's slightly above 0, it's non-spontaneous. So the delta G being 0, that's really when we have our threshold between spontaneous and non-spontaneous. So if I set delta G equal to 0 and I place the delta H minus T delta S, if I rearrange that equation, I can add T delta S to both sides, and I have T delta S equals delta H. And I can now divide both sides by delta S, and that allows me to figure out the temperature for the reaction where it becomes spontaneous. So I can convert the delta H into joules, convert the delta S into kilojoules, but as long as the units match up and are able to cancel, we can then solve for the temperature at which the reaction becomes spontaneous, and then you just have to apply to the situation. So if I have a temperature that is slightly above what the temperature is at 0, that does not mean that it's automatically going to be spontaneous, because there are certain situations where it's spontaneous at the low temperatures instead of the high. So it is predicated on what the delta H value is, positive or negative, and or exothermic, and also what the delta S value happens to be. But that is a way that you can at least figure out essentially the temperature where equilibrium is occurring for that particular reaction. So let's look at a couple of examples to kind of see how we can put all this together. I really like this question because I think this is more of how you could see a lot of these questions being asked to you on the AP exam, asking you to think critically, not just plugging and chugging for the math, but trying to come up with some type of concept. So if you look at this system that's at equilibrium, I have PCl3 plus Cl2 forms PCl5. All three of them are gaseous systems. Notice that I have the delta G being a negative 92 kilojoules. So as a result, I know, and I keep going back and forth between thermodynamically favorable and spontaneous, but please, I know it's a pain, but use thermodynamically favorable in any of your explanations and not the favorable concept. I don't know why they changed that up for College Board, but they did. But I have a thermodynamically favorable process, so again, what we want to think about here is what's happening to my entropy value and also correlating that to what's happening to the enthalpy. So in this particular situation, notice I have all gases, so that first little tiebreaker can't be used because I don't have a different state of matter. So now I go to the second thing and I look at how many moles of those gaseous reactants and products I have. I have 2 moles of gaseous reactants. I have only 1 mole of gaseous products. So as a result, I'm getting more ordered in my system because I have less probable positions for those molecules to exist in. So that would tell us that we would have a negative value for delta S. So in order for the delta S to now be a negative value and to still have a negative delta G value, again, thinking about delta H minus the T delta S, knowing that this is a negative value and this is a negative value, you should be able to infer whether or not delta H is exo or endothermic. And because I have a negative T delta S, I know that that product here would end up being a positive. So in order for delta G to be a negative value, delta H must also be a negative value. So it has to be exothermic. So now when it says what will happen to the ratio of the partial pressure of PCl5 to the partial pressure of PCl3 if the temperature is raised. So now, thinking along this line, I have some negative value here, but since I'm subtracting a negative value for the delta S, and that product is positive, I would have a larger positive product when I increase the temperature. And so as a result of this, I would have a less favorable reaction that would take place. And so as a result, I would have less of the PCl5 that would form. Now, you could also think about this in terms of Le Chatelier's principle. And remember, if I have the heat being an exothermic, I know I could add the heat over here to this reaction, and by increasing temperature, it drives it in the endothermic direction. So the PCl3 would increase, the PCl5 would decrease, and the ratio, again, would become less. So because I'd have less PCl5 that would form in here, again, looking specifically at the ratio of PCl5 to PCl3, that ratio would decrease. All right, so we have one more practice problem kind of dealing with the same type of scenario. So you can see here for the combustion of butane at 298 Kelvin, we have the reaction 2C4H10 plus 13O2 forms 8CO2 and 10H2O. So do you expect delta G to be more or less negative than delta H? So one thing here, you'll notice they don't tell you anything about the delta H value for the reaction. Is it completely necessary? No. However, one thing that you can always tell is that when you have a combustion reaction, you can just think about burning anything, a lot of heat is going to be released, so you know that you would have a negative delta H for that situation. But as I said, is it necessary to know? No, it's not. Because when we talk about this, we want to focus on the entropy. Because with our reaction, delta G equals delta H minus the T delta S, we need to focus on whether or not the delta S is positive or negative. So in this particular instance, I have 15 moles of gaseous reactants. I have 18 moles of gaseous products. So since I'm increasing the number of moles, I know that this will infer that we have a positive value for delta S. And thinking about my equation, since I have delta H minus a T delta S, again, I'm taking a negative and subtracting a positive. So therefore, delta G would have to be more negative. All right, so let's now take a look at a problem where we're actually calculating the delta G and determining the thermodynamic favorability of a reaction based on the values for enthalpies and entropies. So for my equation, delta G equals delta H minus T delta S. Please remember, again, I have a very endothermic reaction, so I have a positive value for delta H. I have a positive value for delta S. Notice the units here are in kilojoules and joules, so I do need to convert from the joules into kilojoules for this particular reaction. So as a result of this, remember, because I have both values being positive, I would need my temperature to be sufficiently large enough in order to make this reaction spontaneous or thermodynamically favorable. So to calculate, I would have 180.7 kilojoules minus the temperature, which is listed as 298, multiplied by the 24.7 joules. So converting that into kilojoules, again dividing by 1,000, I'd have kilojoules per Kelvin, or should be per mole Kelvin with this. And this product here is right around 7.36 to be exact. So if I took 180.7 and subtracted 7.36, that will give me 173.34 kilojoules. And notice that is a positive value. So since delta G is a positive, it would be an unfavorable process. So the answer would be no, it is not spontaneous. Now, just to use this as a quick illustration, if I wanted to solve for the temperature, again, I could take the T, and take the value for delta H, 100.87 kilojoules, divide it by 0.024 for the kilojoules per Kelvin. And if we did that, 180.7 divided by 0.0247 would mean that we would have to have that temperature all the way up around 7,300 Kelvin in order to make that a spontaneous process. So the odds of this reaction happening spontaneously, pretty much next to nil. So now we're going to transition over to the relationship of free energy to the equilibrium. More than likely, this is going to be the most frequently used relationship between free energy and any of the other components. So make sure that you are comfortable with this. Now, as we go through this, a system can achieve the lowest possible free energy by going to equilibrium, not by going to completion. So we have two possibilities when, as you saw in one of those previous slides, in this position here, if I'm just thinking about a ball rolling down a hill, again, gravity's pulling it on it in this direction. It would also be pulling on it if it was going in this direction. So it can be spontaneous either in this direction or in this direction. And so if we think about the equilibrium being this point right here, then this would be essentially my K. So this could be a situation for Q, and this could be a situation for Q. And if you remember, thinking about Le Chatelier's principle, these reactions will always move in a direction to reestablish equilibrium. Find the lowest energy position possible for the system. By having the system with the least amount of energy, that means that it has the maximum amount of energy that it can donate to some other process or give away, and that's that free energy concept. Whereas if I have a reaction that just goes to completion, there is no reversible process. So again, it can go down at some point here, but then the reaction stops. If I have the reaction trying to go in the other direction, it would never be possible to have it be spontaneous. So you have your equilibrium reactions. Again, this is the lowest amount of potential energy if you think about it over here on this side. since it has the lowest amount of potential energy for the system, that means that it has the greatest amount of energy to give away for work. You can see here just another way to look at this diagram. Again, my delta G value on the y-axis. When I hit equilibrium, that gives me the lowest, most negative value of delta G, or the least positive. I could have the equilibrium position occurring here as well, but now notice the direction of the arrow again, going towards that lowest energy position possible. That gives us the spontaneity moving in the reverse direction in this case, which gives us the overall graph of the two being combined together, with the low point on the graph telling us where the equilibrium lies for that particular reaction. So the equilibrium point occurs at the lowest value of free energy, essentially the most negative value for delta G that is available to the reaction system. Well, what if we need to predict the direction that the reaction is going to move to establish equilibrium? If you remember back in our equilibrium unit, to predict the direction of the reaction, we would compare the value for Q to K. And so we said that if our Q value was greater than K, then I had too much of the product compared to the reactants, and so I know that the reaction would shift to the left. If my Q was less than K, then I had too much of the reactants compared to products, and the reaction would shift to the right. And if Q was equal to K, then we knew that it was at equilibrium. Well, we can use the values for delta G and compare them to the non-standard conditions, what the delta G value is, to determine the direction that the reaction would move. So in this type of scenario, the delta G naught, that is for your equilibrium standard state conditions. The delta G, those will be your non-standard state conditions. So that would essentially be the value for Q, whereas the delta G naught would be your value for K. So again, thinking along those relationships, we could make the comparison where we know that the delta G is equal to the RT ln of Q over K. And we can establish that since I have this as a fraction, I could say that the delta G is equal to the RT for the ln of Q minus the RT for the ln of K for that particular system. And so now we could compare the value if the delta G value is greater than the delta G naught value. Now in that particular situation, thinking along the lines like this, that would mean that my Q is greater than my K, and so as a result, I would have my reaction shift towards the left. If my delta G is less than my delta G naught, now that would be the same thing as saying my Q is less than the value for K, so I know that that means that my reaction would now shift towards the right for a particular reaction. And if delta G is equal to delta G naught, then that means that it's at the equilibrium for a particular reaction. So we can use those values when I compare Q over K. If it's equal to 1, then I know that the ln of Q over K would be equal to 0, because the ln of 1 is equal to 0. So the RT product would no longer be applied, because that anything times 0 would be 0. So I'd have the delta G equaling the delta G naught. So we have a few different scenarios that we can look at to kind of help us figure these different reactions out. So again, when I look at this, if I have the Q over K being less than 1, again, meaning that I have too much of the reactants compared to the products, then the reaction would move spontaneously to the right. And if I have Q over K being greater than 1, then my ln of Q over K would be greater than 0 times the RT would give me, therefore, a too large value for the delta G, and it would move to the left spontaneously. So again, we can look at these relationships here for this basic equation to help us determine which direction the reaction is going to shift. I know this is a tough concept, so that's something that I will talk about more in class as we move forward. So just a quick synopsis for this, because I know this is the hardest concept of the delta G component for you guys to figure out. So again, if my delta G naught is 0, then my K value would equal 1. So again, ln of 1 would be 0, 0 times the RT. There you go. If my delta G naught is less than 0, again, I have that spontaneous process, thermodynamically favorable in the forward direction. That means that my K value would have to be greater than 1 because I'd have more products found at equilibrium compared to reactants. And then finally, if my delta G is greater than 0, then that means I have a positive delta G, non-spontaneous in the forward direction, so therefore spontaneous in the reverse direction. So I would have more product compared to, or more reactants compared to products at equilibrium, and I would have a value that would be less than 1 for the K. Now, when we try to go in and solve for K from the delta G value, remember, if I have this equation, delta G equals negative RT times the ln of K, remember that the inverse of the ln is raising e to a certain power. So in this case, I would have e to the negative delta G, again, I got the negative from the RT, divided by that RT value. Please just remember that the R, again, is in joules. So comparing that to the delta G in kilojoules, just make sure that you convert it. Otherwise, you're going to get your number messed up. So again, convert your joules into kilojoules for your R value. But this would be your equation that you could use to solve for the equilibrium constant based on a given free energy value for a reaction. All right, so I'm going to wrap this up with one problem calculating the equilibrium constant from that delta G value. So if I look at the Haber process here at 25 degrees Celsius, we have N2 plus 3H2 forming 2NH3. So they tell me the standard heat of formation is negative 33 kilojoules, 33.3 kilojoules per mole. I have a negative 33,300 joules per mole. So again, to solve for K, I would take the value for E raised to the negative delta G divided by RT. So when I look at this problem, I would have the negative G, which is the negative 33,300, and I'm taking the negative of that, so that's going to make that a positive. So I have a positive 33,300 joules divided by 8.314 and 298 Kelvin. So when I plug those values in, I end up getting 13.4 for that value. And so for the equilibrium constant, I can take E and raise it to the 13.4 value, and that will equal 687,336. And so as a result, we can approximate that to be roughly 7 times 10 to the 5th power for the value of K. All right, so that is going to conclude this lecture video. As I was saying in class, I'll go over a little bit more with that last slide that we did, where we're looking at the non-standard conditions and how that relates to the equilibrium and to the predicting the direction of the reaction using Q. So I know that's a tough concept, so I'm going to spend probably a good 20 minutes in class tomorrow going over some examples of that to kind of help you understand that process. So have a wonderful afternoon, and I will see you guys tomorrow in class.